Welcome to the Genetic Engineering and Biotechnology News webinar series. Our presentation today is entitled Automating MRM-Based Protein Quantification. I'm Jeff Bogaliskas, Technical Editor for GEN, and I'll be the moderator for today's webinar presentation. Multiple reaction monitoring, or MRM, using mass spectrometry is a highly sensitive method for quantifying protein or peptides in complex biological samples. In contrast to traditional mass spectrometry, which attempts to detect all proteins within a biological sample in an indiscriminate manner, MRM is highly selective and targeted, allowing researchers to calibrate an instrument in order to search for peptides or protein fragments of interest more precisely. This approach allows for greater specificity, sensitivity, speed, and quantitation of analytes. The MRM platform technology allows for the targeted analysis of proteins rather than sifting through enormous amounts of data that can typically result from less focused methods. Our first speaker today is Tasso Miliotis, Associate Principal Scientist at AstraZeneca in Malmö, Sweden. Dr. Miliotis will discuss the methods and strategies he's devised for automated MRM protein sample preparation and quantification. Dr. Miliotis will be followed by Steve Murphy, Director of AssayMap Applications Development for Agilent Technologies. Dr. Murphy will discuss in greater detail the components, protocols, and software associated with the AssayMap platform. Before our speakers get started, I want to encourage you to submit questions for our Q&A session at the end of the presentations. We will try to answer as many questions as we can. Simply type up your question in the Ask a Question box and hit Submit. So, without further ado, let's get started on our webinar. Tasso, take it away.
Thank you, Jeffrey, for the introduction. Let me start directly with the outline of my presentation. First, I will provide an introduction to targeted protein quantification and highlight some of the key features of targeted mass spectrometry. The focus of this webinar will be on sample preparation, more specifically how to tackle the challenges in targeted proteomic workflows and how to replace typical manual multi-step protocols available. In order to obtain more precision as well as higher throughput, automation is a prerequisite. The Translational Science Lab at AstraZeneca R&D Malmö have developed a fully automated sample preparation workflow for the robust quantification of human plasma proteins using the Bravo AssayMap platform from Agilent Technologies. During the next 30 minutes, I will present some results that we have obtained using this versatile platform. Before discussing targeted mass spectrometry, I would like to spend some time talking about how the dependence of immunoassays can limit the use of potential biomarkers in pharma R&D. Immunoassays are available for about 10% of the human proteome. As we all know, the quality of antibody kits are extremely variable. Moreover, multiplexing typically requires extensive optimization. If an antibody is not commercially available and you want to develop a sandwich ELISA, you need to produce and purify 2 epitope-matched antibodies, which can take up to 12 months. This extensive development time translates into high costs, and at the end of the day, there is no guarantee that the immunoassay works. This slide I've borrowed from Dr. Lee Anderson. It illustrates one intrinsic property of immunoassays, namely the black box concept. Being a mass spectrometrist, I confess that I'm biased here, but nevertheless, I do not like the fact that you don't have a clue whether an immunoassay suffers from unrecognized interferences. What forms the immunosandwich or prevents its formation is not directly visualized, since immunoassays do not provide you with a molecular microscope, such as a mass spectrometer. The false negatives illustrated on the slide are all cases where the epitope on the antigen recognized by one of the antibodies is covered up. In the first example, by another protein forming a complex with the antigen, or in the second example, by an endogenous autoantibody to the antigen, or finally, as in the third example, where the epitope is missing because that part of the antigen protein has been cleaved off. In each of those cases, the sandwich does not form and no signal is generated. The false positive scenario is illustrated by the fourth example. HAMA stands for Human Anti-Mouse Antibody. It turns out that lots of people normally have antibodies in their blood against mouse IgG, and these endogenous human antibodies can make a link between the capture and detection antibodies of the immunoassay in cases where the assay antibodies are mouse monoclonals, hence generating a false positive signal. Having said all this, I want to emphasize that immunoassays indeed are a valuable analytical tool once they've been validated. They are remarkable in being capable of quantifying proteins at the low picogram per milliliter level in undepleted human plasma with the presence of other proteins that differ more than 10 orders of magnitude. Mass spec of today, no matter how sophisticated they are, cannot compete with immunoassays regarding LOQs. Targeted MS technologies typically involve triple quadrupole instruments. These types of mass spectrometers have been used and refined for over 4 decades and represent the most robust instruments available for targeted quantification. Recently, high resolution, high mass accuracy MS systems, once confined to data-dependent discovery work, are increasingly being used for targeted MS analysis with benefits of higher specificity and lower potential for false positive quantifications. This type of instrument is very interesting but will not be covered here. The basic principle of targeted MRM analysis on a triple quad instrument is illustrated on this slide. Briefly, the sample must first be subjected to proteolytic digestion. Then so-called prototypic peptides that uniquely represent the target proteins of interest are selected together with the most informative fragment ions, so-called transitions. The prototypic peptides are selected for fragmentation by Q1, and these are subsequently fragmented in Q2. Finally, the known fragment ions are selected for detection in Q3. Stable isotope-labeled analogs of the prototypic peptides are spiked in as internal standards that co-elude with the target peptide, and by comparing the labeled to unlabeled peak areas, a precise quantification of the endogenous peptide can be obtained. Modern triple quads are fast, and more than 100 transitions can be recorded per second in MRM mode, enabling targeted MS analysis of many tens of analytes in a time frame much shorter than the peak widths of their chromatographic elution. Finally, triple quad instruments support so-called scheduled MRM mode, where analysis of subsets of transitions are required during established retention times. This means that an automatic setup of multiple time segments is obtained to maximize the dwell times of each transition, hereby improving the detection sensitivity. This translates into high multiplexing capability. The highest numbers of proteins quantified during a chromatographic run, including the use of internal standards that I have come across, is 192 proteins, which has been reported by Andrew Percy and co-workers at University of Victoria Proteomics Center. The highest confidence and measurement precision in a complex matrix such as plasma is obtained by adding a known concentration of an isotopic labeled analog of the prototypic peptide being measured. The labeled internal standards fragment identically to their native counterparts but are distinguished in the MS and MSM spectra by their increased masses. The confidence that the correct peptide is measured using just a few fragment ions is increased by the requirements that the isotopic labeled peptide co-elude with the endogenous peptide and that their monitored fragment ions have the same relative abundance. One of the major challenges of targeted peptide analysis is the prevalence of interferences originating from other peptides and small molecules in the sample matrix. After triple digestion of the plasma samples, hundreds of thousands of peptides are produced. Interferences manifest themselves in 2 ways: ion suppression and transition interference. Suppression decreases the ion current response in an unpredictable and unreproducible way. The resolution of a triple quad instrument is typically 1 Dalton, which means that transition interferences will occur in a complex matrix such as digested plasma samples. Below on the slide are extracted ion chromatograms of 2 proteins measured in plasma samples that clearly illustrate the benefit of adding isotopic labeled peptide analogs to increase the specificity by enabling the correct assignment of the endogenous transition signal. This slide provides an overview of the experimental workflow that has been used. Briefly, 10 microliters of undepleted human plasma was diluted 1:6 and subjected to denaturation, reduction, alkylation, and triplet digestion. An isotopic labeled peptide mixture corresponding to the prototypic target peptide was added post-triplet digestion. Then the plasma digest with labeled peptide was loaded onto a solid phase cartridge for desalting and enrichment. After SPE, the sample was injected, typically 10 micrograms, onto a reverse phase column coupled to a QQQ instrument. We used a 1290 UHPLC interface to a 6490 mass spectrometer, all from Agilent Technologies. Finally, calibration curves are generated and extracted ion chromatograms of the target peptides are subjected to regression analysis that enables the quantification of the target proteins. The data analysis will be discussed in more detail later. For this development work, a panel of 35 target proteins were used. The concentration range of the protein panel was 4 orders of magnitude, and the molecular weight range of the proteins varied between 7 to more than 500 kilodaltons. The physicochemical properties of the peptides covered a broad range and will be illustrated in the next slide. The 35 peptides used as our model protein panel exhibit a broad range of physicochemical properties. Some of the peptides are hydrophilic, while others are hydrophobic. 3 transitions per peptide were measured, and typically the transition that provided the highest response was used as the quantifier, unless interference problems were discovered, while the other 2 transitions were used as qualifiers. A software called Peptide Picker, developed by UVic Proteomics Center, was used to confirm that selected peptides were unique to the target protein. Moreover, the peptide should not contain amino acids that are susceptible to chemical modification, for example, oxidation of methionine. In targeted proteomics, it is critical that peptides are not only prototypic but also accurately represent the level of the protein. Isotopic level peptides, analogs to the prototypic peptides, will from now on be called cis peptides. Cis peptides were synthesized, purified, and characterized. Standard FMOC chemistry principles were applied. The concentrations of the cis peptides were determined by amino acid analysis and capillary zone electrophoresis. An average of 95% purity was determined for the 35 cis peptides, and this information was incorporated into the calculations when determining the endogenous protein concentration level. The 35 target protein panel is commercially available as a kit from MRM Proteomics Incorporated. Included in the kit is the lyophilized balanced cis peptide mix to create the standard curves and a reference human plasma sample that is digested. The cis mix is subsequently spiked into this digested reference plasma sample, and the calibration levels are created. Moreover, a comprehensive user's manual, including LC and MS parameters, are supplied. Reference LQ values for each protein is also provided in order to evaluate the sensitivity of the assay. Finally, a major benefit was the data analysis software Qualis-SIS, which I will come back to in the next few slides. Although trypsin also was supplied in the kit, we prefer to use our sequencing-grade modified trypsin from Promega. This slide illustrates the analytical parameters used for the LC-MRM analysis. Typically, 10 microgram of plasma digest was loaded onto a reverse phase UHPLC column that was operated with a flow rate of 0.4 milliliters per minute, and a gradient time of 27 minutes was applied. 3 transitions per peptide were measured, which means that in total 210 transitions were measured for the 35 target peptides and their corresponding cis variants. Monitoring that many transitions requires a scheduled MRM approach, which means that reproducible retention times are a prerequisite. Typically, a CV of below 0.15% was obtained for the monitored target retention times. A typical extracted ion chromatogram with only the light-heavy quantifiers is depicted at the bottom of the slide. Standard curves were generated by spiking the reference plasma digest with a mixture of cis peptides at different concentrations, while the endogenous NAT concentration of the target peptide was constant and therefore used as the internal standard when creating the calibration curves. By using this curve generation technique, you can plot the relative response, that is cis divided by NAT, as a function of the cis peptide concentration. The patient samples were, on the other hand, spiked with a constant cis concentration, and the relative response, cis divided by NAT, is plotted as a function of the relative concentration. The regression actuation obtained from the standard curve is then used to determine the endogenous protein concentration. The whole concept of the described quantification strategy is to keep the matrix component of the calibration curve very close to the matrix component of the experimental samples, that is, keeping the potential interference substances constant and hereby obtain very accurate LOQs. This data analysis strategy is discussed in detail by Percy and co-workers in the paper highlighted on this slide. The control plasma was tested extensively in the quantitative method development for transition interferences and response ratios. In this evaluation, the spiking ratio of the cis peptides were adjusted such that they correlate to their NAT counterparts with 1-to-1 ratios being sought. The Proteomics Center at the University of Victoria has developed software that automates the generation of peptide standard curves as well as the calculation of the endogenous protein concentrations in patient samples. It also provides you with specific attributes such as the LOQ and the dynamic range. Apart from the automation and speed of processing the data for curve interpretation and results extraction, I personally like to interactively examine the data when changing various analysis parameters, such as the threshold for precision accuracy criteria or changing the calibration level removal strategy. Altogether, this streamlines the comparison and enables the final analysis parameters for a given assay to be more rapidly defined. The development of the Qualis-SIS quantification software has recently been published by Mohammed and co-workers, and all the details can be found here. Let us talk about the Bravo AssayMap platform that has made my life in the lab so much easier. The AssayMap system comprises three major technological components. First, we have the disposable microchromatography cartridges. More information about the cartridges will be provided later. The second component is the Bravo liquid handler modified with a 96 syringe probe liquid handling head that uses positive displacement pipetting to strictly control flow rates of liquids driven through cartridges. All 96 syringes are driven in unison, and flow rate can be reliably controlled down to 500 nanoliters per minute. The standard configuration also includes deck position with Peltier heating cooling station, a shaker, and a gripper attachment on the AssayMap head to move around plates during protocols. The third component is the simple user interface, which I think is key for a successful implementation of the AssayMap to a wide lab population. This allows assay development to focus on chemistry rather than how to program a robot. You just type in the flow rate, volumes, and whether or not to conduct certain steps. By building simple, task-oriented, modular protocols, single steps to entire sample preparation workflows can be addressed without the need for scientists to become automation engineers. Within 15 minutes, you know how to perform a solid phase extraction. Let us take a closer look of the AssayMap head and the corresponding cartridges. The AssayMap cartridges at the upper left are designed for microscale purification applications and utilize a 5 microliter chromatographic bed that is slurry packed with various resins. The sample cup of the cartridge is a portion of the cartridge that mates to the probes on the AssayMap head. The AssayMap head at the upper right has 96 syringe probes made of PEEK, which are all driven in unison. The cartridges can withstand a pressure in excess of 200 psi. The probe profiles were engineered to mate with the cartridge cup, enabling a liquid-tight connection to be made at the inlet seal. On the bottom right, it is illustrated that the AssayMap head can perform aspirate and dispense tasks with mounted cartridges with bare probes or with disposable pipette tips, depending on the protocol used. The AssayMap head therefore functions both as a liquid handling head and as a head to perform solid phase extraction using cartridges. Here, this slide illustrates the comparison between the manual protocol provided by MRM Proteomics and the developed automated protocol using the AssayMap. The timelines provided are approximate and valid when 50 samples are being analyzed. Of course, it will take longer time for the manual protocol when analyzing more samples, while the automated protocol is not affected due to the parallel nature of the AssayMap. The manual protocol on the left side was included in the 35 protein panel kit. Sodium deoxycholate is used as denaturant. Denaturation, reduction, alkylation, and quenching takes about 4 hours if you're manually handling a batch of 50 samples. In comparison, the corresponding time for the automated protocol requires about 1.5 hours. Note that we have exchanged the denaturant to urea in the automated protocol. The main reason being that we want to avoid the precipitation step, the centrifugation step, as well as transferring the supernatant that is mandatory when using sodium deoxycholate. The samples are trypsinated overnight for 16 hours in both protocols. A solid phase extraction step to dissolve the sample is conducted in both protocols. Manual SPE is performed in the manual protocol, and the eluate is subjected to lyophilization overnight and then redissolved in acidified water to make it compatible with reverse phase liquid chromatography. In contrast, the AssayMap protocol eliminated the need for lyophilization. We are loading the same amount of plasma digest, that is 100 micrograms, as in the manual protocol, but we are using an elution volume of typically 10 microliters instead of 200 microliters used in the manual protocol. Even though we are eluting off the tryptic peptides with up to 70% acetonitrile, we can inject the effluent directly onto the reverse phase LC-MRM system. The trick is that we can afford to dilute our sample and make it compatible with reverse phase chromatography. In fact, the enrichment factor of the AssayMap can be up to 100-fold, since you can load as much as 1 milliliter onto the cartridge. This large enrichment capability is a unique feature of the AssayMap. This slide describes the details of the two different cartridges, both commercially available, that were evaluated. The C18 cartridges are packed with high-capacity silica-based C18 resin with a pore size of 150 angstrom. This resin is stable from pH 2 to 8. The RPS cartridges, where RPS stands for reverse phase small pore, is a non-polar styrene divinyl benzene polymeric resin that is underivatized and is hydrophobic due to the chemical nature of the polymer. This resin has a pore size of 100 angstrom and is stable from pH 1 to 14. The loading capacity of these cartridges was about 150 micrograms. This is an overview of the tested elution conditions that were evaluated on the two different cartridges mentioned. Elution volumes of 10, 15, and 20 microliters were tested. It was shown that the 10 microliter elution volume was sufficient to elute off 35 targeted peptides when loading 100 micrograms of plasma digest onto the cartridges. Moreover, we tested different elution strengths as well as compared formic acid against trifluoroacetic acid. Here are some results obtained when comparing the C18 versus the RPS cartridge. These results were obtained when using an elution condition of 60% acetonitrile with 0.1% formic acid and an elution volume of 10 microliters. The proteotypic peptides corresponding to the 4 proteins on the left were the most hydrophilic peptides in the panel, while the 4 most hydrophobic proteotypic peptides are shown to the right. There is not a big difference of the relative response measured in the eluates of the C18 and RPS cartridges, particularly not for the hydrophilic peptides. There is a tendency that the hydrophobic peptides provide a higher signal when using the RPS cartridges. However, by changing the elution conditions of the C18 cartridges to 70% acetonitrile and replacing formic acid with TFA, we obtained very similar results between the C18 and the RPS cartridges. Extended recovery studies are planned to be performed in the near future. Preliminary data suggests that the recoveries vary between 87 to 97%. Jason Russell and co-workers at Agilent Technologies have shown that the recovery of hydrophobic peptides was reduced when the load mass decreased below 10 micrograms. However, the recovery, even when low, was reproducible. We have confirmed these findings with our peptide panel. Finally, the capacity and binding characteristics were nearly identical between the C18 and RPS cartridges. Up to 150 micrograms could be loaded on each cartridge without exceeding the binding capacity. We noticed that hydrophilic peptides became competitively displaced as the load increased above 150 micrograms, and this was pronounced with the RPS cartridge. This slide illustrates the optimized SPE protocol for the C18 cartridges. You can read the details yourselves. The rationale for choosing the C18 cartridges instead of the RPS cartridges was that the C18 cartridges exhibit slightly better retention of hydrophilic peptides as the load amounts were increased above 150 micrograms of plasma digest. As mentioned previously, in order to obtain the same recovery of the hydrophobic target peptides, we had to increase the acetonitrile from 60 to 70%, while at the same time replace formic acid TFA. Note that the flow rate during loading takes, in this case, about 40 minutes to complete. We have not tested the effect of loading at a slightly higher flow rate of 20 microliters per minute, but this will be evaluated. During elution, it is recommended to use a flow rate of 5 microliters per minute, but preliminary results indicate that an elution flow rate of 10 microliters per minute gives about the same relative response of our 35 target peptides. Finally, worth mentioning again, the small elution volume provided by the AssayMap enables you to dilute the effluent tenfold, hereby permitting a direct injection of the effluent onto the reverse phase liquid chromatography system, circumventing the subsequent speed vacuum or lyophilization step. This slide provides you with the overall picture of the automated MRM workflow using the AssayMap platform. We evaluated the reproducibility by analyzing 20 identical human plasma samples that were subjected to a fully automated protocol. The protocol involved the denaturation, reduction, alkylation, quenching, dilution, over-nitrogenation, and subsequent solid phase extraction using the AssayMap robot. In fact, even the calibration levels were diluted using the AssayMap. 3 calibration curves were required, and then the 20 samples were analyzed by LC-MRM. The data analysis was performed using the Qualis-SIS software. Here we have plotted the CV range of the 20 identical experimental samples. The results obtained were excellent, with CV values for the relative response and endogenous protein concentration predominantly lying below 9%. One target peptide exhibited an elevated CV of 16%. This slide illustrates how the data is presented by the Qualis-SIS software. In this specific case, I have extracted the calibration curve data of apolipoprotein A1. As you can see, all the calibration levels pass the qualification requirements as specified by the criteria at the bottom left side. The LOQ of ApoA1 was determined to 16 femtomole per microliters, and the dynamic range was, in this case, 10,000. The next slide shows the determined concentration of ApoA1 in 20 plasma samples, although only 8 are visible here, of which all originate from the same donor in order to measure the repeatability. All the samples were subjected to the entire sample preparation protocol as previously described, and for ApoA1, the CV was calculated to 4.5% across the 20 samples. Here are the summary of the results obtained using the fully automated digestion and SPE protocol and the subsequent measurement of human plasma proteins. 35 plasma proteins were quantified, where the average dynamic range obtained by the calibration curves was 500, and the highest dynamic range of the protein measured was 10,000. The LOQ range varied from 5 nanomolar up to 11.5 micromolar for albumin. The repeatability for the endogenous protein concentration measured as the coefficient of variation was predominantly below 9%, with the exception of alpha-1b glycoprotein that had a CV of 16%. In conclusion, MRM with a cis-peptide approach has emerged as an indispensable and precise tool for protein quantification, and it is used extensively in our laboratory for the validation of biomarkers. The AssayMap platform has significantly improved the efficiency of the Translational Science Lab at the AstraZeneca Mölndal site. Not only the capacity of processing up to 384 samples per batch, but more importantly, skilled labor can use their precious time more efficiently. The precision of the robot is outstanding, and the AssayMap does a perfect job, regardless whether it's Monday morning or Friday afternoon. Finally, since you can load up to 1 milliliters onto the cartridge, you can theoretically obtain an enrichment factor of 100-fold, provided that the loading capacity of 150 microgram of the cartridge is not exceeded. Remaining future experiments to be performed, including a more rigorous investigation into the inter-assay precision with standard curves and individual samples prepared and processed on different days by different operators. Such work is being planned together with the Proteomics Center of the University of Victoria, and the final comparison to the manual prep workflow will also be conducted and presented. Finally, I would like to acknowledge the following people. First of all, my master thesis student, Martin Urbom, who actually performed all the work in a systematic and efficient manner. Steve, Jason, and Zach for great collaboration, for listening to their customers and implementing new features to the in-solution digestion as well as the SPE protocols. Andrew, who provided me with slides and feedback to this presentation. He also spent a week in our lab transferring knowledge about the manual sodium deoxycholate protocol and introduced us to the Qualis-SIS software. Nicole for providing us with the protein peptide input files to be used with Qualis-SIS. Christoph for visiting our lab and generously sharing his extensive experience and knowledge regarding MRM protein quantification. Last but not least, Gary for sponsoring us with the workflow kit of the 35 protein panel. Thank you very much for your attention.
Great. Thanks, Tasso. That was really informative. Before we move on to Steve's presentation, I just want to remind everyone once again about submitting questions through the Ask a Question box. Both Tasso and Steve will be available to answer your questions after this final presentation. Okay, let's move along. Steve, as they say, the floor is now yours.
Great, thank you. Hello, everyone. Thank you for attending this webinar. Tasso just provided a very nice example of the kind of results that can be achieved using AssayMap Bravo. I'd like to take a step back and give a little bit more detailed overview of the AssayMap platform and how it can help you automate your sample prep workflows. So on this slide, you can see the platform is composed of three basic elements. The first being the Bravo liquid handler with an AssayMap head containing 96 probe syringes. The second is the AssayMap cartridge, which mates to the probe syringes. And the third is the simple user interface that controls the AssayMap Bravo. In the next few slides, I will go into more details about each of these components. The AssayMap Bravo is a high-precision liquid handler equipped with an AssayMap Bravo head containing 96 probe syringes arranged in SBS footprint so as to work with standard 96 well plates. When the probe syringes engage the cartridges, a tight seal is formed between the probe syringe and the cartridge with no air gap. Instead, there's a liquid-liquid contact such that each of the 96 syringes can act as a syringe pump to move liquids across the packed column beds of the attached cartridges. This allows precise unidirectional flow across the cartridge bed. All of these features allow chromatography in a small volume parallel format. The benefits of these features is highly reproducible results, quantitative binding and elution, highly efficient washing, extremely small elution volumes and thereby concentration, and the ability to process anywhere from 8 to 96 samples simultaneously. Next, I would like to focus on the AssayMap Bravo head. The top of the slide shows a closer view of the AssayMap Bravo head with its 96 probe syringes. The left side of the slide, you can see the probe syringe and its plunger. Note that the plunger design gives a nearly zero dead volume in these syringes. On the bottom of the slide, you can see the cartridges seated on the probe syringes. Please note how the bottom of the probe sits on top of the cartridge bed. And lastly, on the bottom right, you can see a cartridge beside a U.S. quarter to give a frame of reference for the size of the cartridges. Next, we turn to the AssayMap cartridge. As you can see in this picture, the cartridge bed is at the bottom of the cartridge and is held in place by a top and bottom frit. The cartridges have a 5 microliter bed volume. Each cartridge is back pressure tested as part of the manufacturing process to ensure consistently packed beds. The cartridges can be packed with a variety of different resins. These features result in highly reproducible results, consistent binding capacity, and the ability to address a wide range of workflows. The last major component of the platform is the user interface. This interface is designed to be easy to use by bench scientists. The interface and the underlying program have been optimized so the user only has to input a small number of key parameters required for their particular experimental conditions. The interfaces are harmonized across different applications, so once you know how to use one application, moving to another is very intuitive. Using the software requires minimal training, so it can be rapidly adopted in the lab. Protocol transfers between people and sites is simple and dramatically decreases the risk that information is lost or miscommunicated. The ability to rapidly set up and run experiments allows scientists to do more value-added work while the robot does the tedious work. Next, I'd like to show a cartoon here that is basically the kind of workflow that Tasso talked about. Namely, a protein mixture is denatured, reduced, alkylated, and digested using the AssayMap in-solution digestion protocol. Then the resulting peptide mix is cleaned up using the AssayMap peptide cleanup protocol and reverse phase cartridges. Finally, samples are analyzed by LC-MS. This cartoon shows the AssayMap Bravo has the flexibility to address other similar workflows. Antibodies are purified from a complex mixture using the AssayMap Affinity Purification protocol with protein A cartridges. The purified antibodies are then digested using in-solution digestion, and the resulting peptides are cleaned up using the peptide cleanup application. Finally, the cleaned up peptides are used for antibody quantification and/or characterization. This slide shows an example of the performance of the first step of the workflow I just described. The top figure shows the result of an experiment where various masses of human IgG1 are loaded onto AssayMap protein A cartridges, then washed and eluted using the Affinity Purification application. The microgram of antibodies loaded in the cartridges are plotted on the x-axis, and the microgram of antibodies recovered in the elution is plotted on the y-axis. One can see that recovery is quantitative until one nears the capacity of the cartridge. In the bottom figure, 100 micrograms of antibody is loaded onto each of 96 protein A cartridges in parallel, washed and eluted using the AssayMap Bravo. The absorbance from each well of the elution plate is plotted, showing the kind of reproducibility that can be achieved with the Affinity Purification application. Next, we look at the results of doing an entire workflow of purifying antibodies from 96 identical cell culture supernatant using the Affinity Purification application, followed by denaturing, reducing, alkylating, digesting the purified antibodies using the AssayMap in-solution digestion application, which is then followed by cleaning up the peptides using the peptide cleanup application. These samples are then analyzed using an Agilent HPLC and QTOF. The table on the top of the slide shows percent CV for the extracted ion chromatogram peak area for each of 6 peptides across the 96 samples. Shown in the bottom of the slide is an overlay of the extracted ion chromatograms for the first 12 of the 96 samples for the 6 different peptides. This same basic experimental approach was used to generate data on this slide, but this time during the digestion step, 3 different enzymes were used in parallel. The percent sequence coverage was determined for each enzyme, as was the cumulative percent sequence coverage for all 3 enzyme digestions. In summary, the AssayMap Bravo platform provides highly reproducible results for workflows by decreasing the intra-experiment, inter-experiment, and inter-person variability from the sample prep portion of the workflow. It allows scientists to stop doing tedious work and start spending their time on higher value work. The software is easy to use, so you can generate actionable data instead of spending time learning how to use the software. And it is a single platform that addresses a wide and ever-growing variety of sample prep needs. And to finish, I would like to acknowledge the people responsible for doing much of the work shown on this presentation. And with that, I would like to hand it back to Jeff.
That was great. Thanks, Steve. I appreciate that. And just to finalize, I'd like to thank both Tasso and Steve for giving 2 great presentations today. And before we start the Q&A session, I just want to let everyone know that this is your final chance to submit questions for our speakers, so hurry up and submit them now. I also want to let you know that a post-webinar survey will deploy shortly in your presentation manager. You may need to disable your pop-up blockers. So please take a few moments and complete the short survey. We really value your feedback. All right, let's begin the Q&A. It looks like we have a bunch of questions that are already starting to roll in, so we'll try to get to as many of them as we can. Okay, great. Thanks for a great presentation again, guys. And we're going to get to our first question. So our first question is for Tasso. Tasso, why did you spike in the internal standards after the triptych digestion?
Okay, thank you. Well, that's a good question. Normally, it's best to add internal standard as early in sample preparation workflow as possible to compensate for any variation during the sample preparation. So, I mean, hence the addition of the SIS mix prior to triptych digestion would seem to be the preferred choice. However, it has been shown in the literature that when the cis peptides are added prior to digestion, the peak area ratios, that is light compared to heavy, can be elevated when compared with those obtained with post-digestion addition of the cis peptides. Moreover, the degree of the peak area ratio increase has been shown to vary depending on the peptide and was not predictable. So in conclusion, this ratio increases suggest that internal standard peptides are either being degraded or perhaps chemically modified over the course of the digestion. So in order to avoid this source of variation, we prefer to add the peptides after the post-digestion.
Okay, great. We have another question up here, and wants to know how many proteotypic peptides are used to quantify proteins. And that's for you.
Well, in this specific work, we used only one. Typically, I would say, if you have, I think you should have more than one. We have two, but the problem is, and this will always be a problem. Some peptides, well, in theory, the results should be the same, but for reasons like during tryptic digestion, the peptide liberates differently or whatsoever. You will most likely have a portion of peptides, proteotypic peptides, if you're monitoring two per protein, that will have quite different values in your subsequent quantification, and you then take typically or normally the highest peptide concentration that you receive.
All right, and I think for our next question, Tasso, someone wants to know, can the micro cartridges be reused?
We have not really tried this, but maybe you can reuse them when you're doing method development. Possibly, we have performed consecutive elutions of the micro cartridges, and they are very clean. Hardly no signal is detected, but I think they are designed to be single use. But maybe you have to try, I think. But for real samples, they're single use.
Okay. And I think for the moment, I think this will be the last question we have for Tasso. Maybe some more roll in. But Tasso, have you evaluated the recovery using the 35 protein panel of the different cartridges?
Yes, we have some preliminary data. We have to repeat it, but yeah, as I mentioned in the webinar, preliminary data suggested the recoveries were between 87 and 97 of these specific peptides, and also we noticed that the recovery of hydrophobic peptides was reduced when the load mass decreased below 10 microgram. However, the recovery even then was, even when low, was reproducible.
Okay, great. Thanks, Tasso. Steve, we have a couple of questions that have come in for you. I think that people like to answer. So the first one is, you talked about the easy-to-use software. Does this mean that this is a black box that the user is locked out of, or can the user build their own custom protocols?
Yeah, the AssayMap applications and the user interface are built on a vWorks liquid handling software, and the software is fully accessible to the user if they have the proper administrative privileges. So the answer is you can absolutely write your own protocols if you choose to. In addition, if you have administrative privileges, you can use the forms that and control which of those inputs are locked or unlocked. So even though that we've worked to minimize the number of inputs, if the administrator chooses to, you can lock it down so that there's only as few or as many available to the end user.
Okay, great. So our next question for Steve is, can the AssayMap Bravo also be used for standard liquid handling?
Yes, the Bravo is the AssayMap Bravo is a standard Bravo liquid handler with an AssayMap head. So the liquid handling can be performed with the AssayMap Bravo head and pipette tips, or you can swap out the AssayMap head for any of the 3 standard liquid handling head. It only takes a few minutes to make that change.
Okay, great. We have one more question for you, Steve, and that's, can you confirm that the AssayMap robot can do protein A purification, digestion, and SPE cleanup of peptides?
Yes, that we definitely can do that. The in solution, the digestion part is pretty much does not use cartridges, but we include that to make, because we want to enable people to do complete workflows.
All right, that sounds great. I think with those questions, with that one, we've come to the end of our webinar. And I'd like to remind everyone that the webinar will be archived for 6 months on our website. So if you missed parts of it, you can watch it again, or feel free to forward the link to your friends and colleagues. I'd like to thank Tasso and Steve again for their informative presentations, and I'd like to thank the audience for their attention and thoughtful questions. And I'd like to give a very special thanks to Agilent Technologies for sponsoring this webinar. And hopefully we'll see all of you again at another Gen webinar in the near future.